Welcome back, Contemporary Math. We are in Chapter 3E. We're going to talk about how numbers can deceive. So we're going to look over a few tests, which are common ways that people are deceived, polygraphs, mammograms, and more. And so we're going to talk about test and testing accuracy and a little bit about what that means. And so we start off with example 1. And we're looking at Jeter versus Justice. So we're looking at two baseball players. Derek Jeter and David Justice. There's their names. And 1995 and 96. And we're going to find out their batting averages. So which player had the higher batting average in both 95 and 96? So this represents 95. This section represents 96. So if we're looking along here, who had the higher average? We're looking at Jeter has 250, Justice has 253. So Justice has more in 95. And if we're looking at the batting average in 96, Jeter has 314 and Justice has 321. So Justice is higher. Justice is higher in both of those. If we look at 95 separate, and then we look at 96 separate from 95, Justice has a higher batting average in both. So a little bit about how they're finding this batting average. They're taking the hits versus the at-bats. So if we take the hits versus the at-bats, you might notice that's 25%. So basically what they're doing is they're going an extra decimal place. They're going 3 decimal places instead of 2. Why? It's because that's what they do with batting averages. Don't really know why they do that with batting averages. There might be a reason, but I'm not personally familiar with why they do it 3 spaces. That you're going to move it 3 spaces, it's going to be 253. So we can look at each of these numbers. What we're doing is we're taking the total hits and dividing by the at-bats. And then instead of a percent, they're doing it times 1,000. So we're going to go 3 decimal places. So this would be a 314 batting average. And this would give you 321 batting averages, the last number that we have there. So if we want to compute the batting average for each player for the 2 years combined. So let's look at Jeter. Let's look at Justice separately. So Jeter, how many hits does he have? Well, Jeter has 12 hits here, and he has 183 here. So 12, and he's got 183. His at-bats were 48 and 582. So I'm getting 195 on top over 630 on bottom. And again, we're going to hits over at-bats. So this one, we're combining the years. So this is his 95 and 96 hits. This is his 95 and 96 at-bats. So at-bats is where I believe where they're stepping up to the plate to go to bat, and the hits is the ones that they actually hit. So we're doing 195 over 630. This is giving me 309.5, so like 309. 0.5, or you could probably just run it out. Let's see. So Jeter's would be about 310. That would be his batting average. Justice, and I got enough room to write it down here. I'll answer C in just a second. Justice, we're going to do the same thing. So we're looking at his hits. He's getting 104 here, and he's getting 45 over here. His total at-bats are 411 and 140. So if I do this, I should be getting 149 over 551. And when I calculate this, the decimal should be about 2704. So we could say he's got about a 270 average. Okay. So we're looking at 310 versus 270. Who had the higher average for the 2 years combined? Jeter was higher. So what happened? If we look at each year separately, we notice that Justice has a higher batting average. But if we look at the 2 years and we combine the 2 years, then Jeter overall is going to have the higher batting average. So one of the things you might notice, and we just did a section on percentages and reference values. Our reference values, these are the base that we're talking about the percentages off of, right? And so if we're talking about this is our base, you might notice that our base is shifting. So part of the reason why this is happening is because our base is shifting. But if I want to explain this inconsistency, what happens when we look at our data separated versus what happens when we look at our data combined is the exact opposite, right? This one Justice is higher, and in this one Jeter is higher. So this inconsistency that we see between like things when they're grouped versus overall, this is known as Simpson's paradox. Don't have a cow. And I think it's on, I do believe we define it on the next page. Yeah, it's defined right on the next page. But if you see this sort of pattern happening and it asks for an explanation for the inconsistency, if you put Simpson's paradox or put this is an example of Simpson's paradox or something along those lines, like this is the explanation. Those are the two words I'm looking for when I ask for an explanation for something like this. I want you to recognize, hey, in groups, it looks different than when it is combined. We get different results. And so they use this word paradox. So this is probably not what let me check. I don't think this is a true paradox. Well, yeah, it's according to the definition, it's true paradox. Yeah, sorry. There are different forms of paradoxes, I guess I want to say. A paradox is something that seems like it cannot be true. Like we get this thing, it's like, well, if we look at the 2 years separately, then this guy's higher. But if we look at the 2 years combined, this guy's higher. That does not seem like something that should be happening. If this guy is doing better in both 95 and 96, we would kind of expect his maybe overall score to be higher when we combine the 2 years. But that's not the case. And so this seems like it should be contradicting itself. But it's really not, and it's really not because we have different sort of sample sizes that we're pulling from. We have different reference values that we're using. And so this sort of thing arises when we have different sample sizes, different reference values, this thing called Simpson's paradox. So you have to look at kind of the size of the things. Okay. So a little bit of side note, like this is a paradox and what we call, or what normal people would call paradox. But there are sorts of things called like logical paradoxes. So we went over logic, so not going too back far into it. But if I want to think about a very simple logical paradox, there's the liar's paradox. And so when we started logic, we said that every statement that we made this assumption that every statement that we made was either a true or false statement. So when we made a statement, it could be verified as either true or false. And this thing is called something called the liar's paradox. So it is something along the lines of this statement is false. And so if we take the statement, and this is a statement, if we assume the statement to be true, then it's true about being false. Therefore, the statement is false. And if it's false, then it's false about being false, which means it's true, which means the statement's true. So if we assume that it's true, then the statement's false. But if we assume it's false, then the statement's true. So this is something that we might say is neither true nor false, or we might say it's kind of both true or false. One way or the other, you're partially correct. But these are things, when I think of a paradox, these are typically the things I think about, like things that are like kind of both true and false and both neither true nor false. And so this statement is false. And so this one is one of those weird things. And I'll say that the part of the reason why this creates that weird sort of thing is because it's self-referencing itself within itself. So when you get some sort of self-referencing mechanism, weird things can really sort of happen. You're talking about yourself, right? It's a sort of meta statement, as Hilbert might say. So that would be like a basic sort of example of a logic paradox. This is something that seems contradictory. How can this be both sort of true and false at the same time, and both neither true nor false, right? So either way we assume this, it's going to be the other thing, or it's going to produce a result that says it's the other thing, right? If we assume it's true, then it's saying it's false. If we assume it's false, then this thing is saying it's true. So the same way that this is utterly confusing, the results of this are kind of utterly confusing, is what this is kind of saying. It's paradoxical. It shouldn't be happening, right? Okay. And so I have Simpson's paradox up here. The definition probably taken straight out of the book. The general case in which a set of data gives different results for each of several group comparisons than when it does when groups are taken together. So what they mean by group comparisons is when we group things into like 1995 and 1996, it was different from when we took both of those years together. So there are a few ways to do these Simpsons paradoxes. They don't have to be years. There is a famous example that comes out of UC Berkeley and their like admissions policy. So there's some interesting sort of things happening there, and probably the way that we talk about gender and sex discrimination. But they basically noticed, the long and short of it, I guess, is they basically noticed that overall there was a sort of like gender discrimination happening at their school. But in short, like each of the departments, their hiring was actually not gender biased. So the individual departments and the people that were actually doing the hiring, their policies weren't biased, but overall they were noticing a bias. And a lot of that sort of like can be attributed to the fact that certain genders like gravitate towards certain majors more, right? And so there were different sizes with acceptance rates, and you end up getting gender discrimination overall. So there's probably some really sort of interesting conversations that could be had if you want to go into the social sciences and like what does it mean to discriminate, right? And so people that don't want to acknowledge that discrimination exists, they're usually really keen to point out, hey, look, each department isn't discriminating, right? But there's the overall picture, like why are people gravitating towards certain majors and those things. There are larger sort of questions there. Then it's kind of hard to say that the discrimination doesn't exist when the numbers aren't adding up, so to speak, right? So if you want to look at that was like the UC Berkeley admissions thing. If you just Google Simpson's paradox, look at the wiki page, I think it comes up in there. It's a pretty common example for this. So here we have another sort of example. In the early 1970s, a medical study in England involved many adult residents from a district called Wickham. 20 years later, a follow-up study looked at the survival rates of the people from the original study. The follow-up study found the following results. Among adults who smoked, 24% died during the 20 years since the original study. Among the adults who did not smoke, 31% died during the 20 years since the original study. Do these results suggest that smoking can make you live longer? Mm-hmm. So I want you to take just like a minute and think about this. So what are they saying here? Among the adults who smoked, only 24% died within the 20 years since the original study. And then among the adults who did smoke, 31% died during the 20 years since the original study. So a smaller percentage of these people died than a percentage of those people. And so from that, they're trying to conclude that smoking extends your life, I guess is what they're trying to say. Something like that, right? So what is wrong with this? Well, it's sort of that thing. It might be based off of the population that you're drawing from. And one thing is that there could be sort of thing, what they call confounding factors. It's a factor that you're not listing here that might explain why things are happening. So one of the things that they said was that non-smokers tended to be older. And so if non-smokers were older, we're going to expect older people to die at like a higher rate than younger people. That's throw some glitter on it. I don't know what else to say. Like, just being honest, like, right, you get older, you get closer to death, right? And so if you're drawing people from an older population, they're obviously a little closer to death than people that are from a younger generation. And so the reflection of death rates increase with age. And actually, if you break it apart, one of the ways that we could see this is if you did break it apart into age brackets. So if you think like this variable of age is confounding your experiment, then one of the things you can sort of do is break it apart. And so if you break into age brackets, and guess what it's going to show if you break it into age brackets? If you break it into age brackets, non-smokers are obviously going to take the cake on there. Take the cake, and they'll eat it too. And so this, if you think about it, if we look overall, if we look into the whole population and we don't account for age, if we just look at the whole population, the non-smokers look really horrible. But if we start breaking things into age brackets, non-smokers are doing way better. And this is sort of like what we know and what we understand, right? Smoking isn't good for you. On a more personal level, like, what want I say? Like 3 out of the 4 members of my mom's family are dead from smoking. So I've seen it kind of firsthand. People suffer from like lung conditions and cancer, and it's not good stuff. So smoking is definitely not good for you. So don't take that away from this class. If anything, hopefully like you're not like taking that away from this problem. Smoking is definitely bad for you. If we group things correctly, we can actually show that and show that we are not just taking into account that some people are older than other people. And so this is another example of Simpson's paradox happening, right? If we look at the group overall and don't break it into age brackets, we're going to see one trend. If we break it into age brackets, and I didn't even give you any numbers here, right, Harley? I gave you these 2 numbers, right? I'm just trying to make you understand, like, it has differing trends depending on how we group things. And sometimes it makes sense to group things, right? And sometimes it makes sense to look at them separated. Sometimes it makes more sense to look at them combined. But this one, it definitely makes sense to look at them separated into age brackets. And so we will see a reverse sort of trend if we do that. And so this is how Simpson's paradox could come into play when we're trying to analyze data. Okay. Now we're going to talk a little bit about mammograms and testing and things of that nature and what that sort of means. And so we will do mammograms. I believe we're going to do also drug tests, which are very similar. And yeah, so there we go. We'll do a lie detector test and we'll do a drug test. And there's one sort of other example that they threw in since I've done these notes last. And I kind of tacked it on the end here. I'll do some political math, I guess. But let's start on a mammogram. So I think we crunch some numbers and then I'll kind of tell you what's going on maybe. So the following table shows a summary of the results of 4,000 mammograms. So if we're looking at the total, this is the total here. And so we have a test over here. And then this is sort of like the reality. So a positive mammogram, there are 428 total positive mammograms. there are 3,572 total negative mammograms, is what this is saying. Now, this is saying the tumor is malignant or the tumor is benign. So if the tumor is malignant, then that means it's bad, it's carcinogenic, it's a bad thing. So there would be 40 total malignant tumors, 3,960 benign. So if we're looking at here, this is the test saying it was bad, and this is the tumor actually being bad. So this is telling you the truth here. These would be bad tests. These would be saying you got it and you really didn't have it, right? These would be saying you didn't have it, but you really did. These would be saying you didn't have it and you really didn't. So this is also true. So you might notice that these two are the true ones. These two are the ones that are not true. Those make false statements. The test failed here and here. It was successful here and here. And so they give us a few things. The table is based on the assumption that 1% of breast tumors are malignant and that mammogram screening is 90% accurate. So it's based off of, they want us to verify these numbers, that 1% of breast tumors are malignant. So where are they getting that from? This is the total that are malignant out of the total. So 40 out of 4,000 is where they're getting that 1%. The other thing they say is this is 90% accurate. So what they mean by this is, given that you have a tumor, what is the odds that this thing is going to detect it? So in order to find this, what we're looking at is the 36 out of the 40 is going to give us the 90%. Okay, then there are a few other numbers. So these are the numbers. This is where they're getting the 1% from. This is where they're getting the 90% from. So this is out of total. How many actually have it? And this is out of how many actually have it. Is it going to detect? Okay. So this sounds, if you step back and you like hear this, you're like, oh, this test is 90% accurate. Sounds pretty good. So what does that mean though? So let's go, and there's actually a few more numbers we should probably verify. We should verify the total. So 428 plus 5, right? 428 plus 35. 72, we should verify that that equals 4,000. So do that in your calculator right quick, or do it in your head, however you want to do it. 3,960 40, 4,000. So there are a few totals we should check, and I put an extra 0 there. So, oops. These should total to this. These two should total to this. Also, they should total across this one. Equal to 428 plus 68 equal to 572. And they should also equal this way. So 36 plus 4 should equal 40. And 392 plus 3568 should be equal to that 3960. So I know I'm writing them probably all outside the table. If you're doing this and they made you fill in some numbers, this is a good way to sort of check that you're filling in the correct numbers. So we have this table. Suppose that a patient has a positive mammogram. What is the chance that she really has cancer? So when they give us information, they're giving us information, and we can kind of sort of narrow this down. Suppose a patient has a positive mammogram. So the second they tell us she has a positive mammogram, I'm looking here, I'm looking along this line of positive mammograms. So I'm not looking at any of these two rows. I'm just looking at this row of positive mammograms. So we're supposing it's on this row. What is the chance they really have cancer? So you're going to the doctor, they tell you you test positive. So we want to know the chance that they really have it. So that would be, this 36 would be the total that really have it out of 428. So the chance that they really have it is 36 out of 428. If we look at this, this is 0.08. And so this is an 8% chance. So let's step back and let's reset what we just said. Suppose that patient has a positive mammogram. So you go to a doctor, they tell you, you have tested positive. What are the chances you actually have cancer, that it is malignant? There's only an 8% chance. So there is still a larger chance, like a 92% chance, you don't have this thing. Okay. So, and if you know anything about this, usually you will go in, and if you get a test and it comes up positive, usually they like to do a second test. We'll talk a little bit more about that. Let's keep doing this and then we'll talk a little more. What is the chance of a positive mammogram given that the patient has cancer? Now the thing that we're given is that they have cancer, which means their tumor was malignant. So we're not looking here, we're not looking here. We are just looking at this first row. We know it is in the tumor is malignant column. We're looking along here. What is the chance that they had a positive mammogram? That would be this 36 out of this 40. So given that they had a malignant, that would be the total 40. What is the chance they had a positive mammogram? The one that was positive mammogram was 36. So now we're doing 36 out of 40. This is giving me 0.90 or 90%. Okay. Let's step back. Let's talk about what this means. So if you have cancer, what is the chance that the mammogram will be positive? There's a 90% chance. Okay. So if you have cancer, there is a really good chance that it will test positive, right? But just because you test positive, does that mean you have cancer? No, those are two different questions. They sound really similar, but they are definitely different questions. This is given that you have cancer, there's a good chance it's going to come up positive. But just because you have a positive test does not necessarily mean that you have the cancer. So suppose a patient has a negative mammogram. What is the chance that she really has cancer? So if you have a negative mammogram, given that it's negative, so now we're looking at this thing where it says negative. We're looking at this row right here. So the total here that we're going to be out of is 3572. So given we are in this row, our total is going to be 3572. What are the odds that it is going to be cancerous or malignant? It would be this 4. So 4 out of 3572. This is like a really sort of small number, 0.11198 or something, which is like 0.1%. And so what does this sort of mean? So if you do get a negative test result, what is the chance that you actually have cancer? It is really low that you're going to have cancer if you get a negative test result. And so I've kind of said it, if we get a positive result, what they usually do is they go in and they will ask you to take another test, because if you have it, there's a good chance that it's going to come up again, right? But if you do get a negative test result, we can kind of reject the fact that you have cancer kind of right away. So if you get a positive result, that doesn't really give you a good chance of assuring that you have cancer, right? But if you get a negative result, it gives us a pretty good odds of being able to reject that you have it, right? And so this is sort of why they like to take a test twice. This test isn't really too good at detecting whether you have it. It's better at detecting whether you don't have it. It's kind of the best way to say it, right? It's better at rejecting it, right, than it is at accepting. And so that's sort of why we go in and take a second test if we come up positive. Because there's not a real large chance that we do have it, but the second we reject it, we can be pretty certain you probably don't have it, right? Even then, right? 0.1% still happens sometimes. Doesn't happen often, but happens sometimes, right? There's always the sort of fluke or the the exception to the rule, right? There's always one of them. 1 in 1,000 on that one, something like that, right? Mr. Francis Seabody organized a crew of a dozen well-trained con artists and burglars. Unfortunately, they were only halfway complete with their caper at the Mesosphere Hotel, Casino, and Resort when police cornered and rounded them up, along with 988 other casino patrons. That seems like a nice round even number for some odd reason. The police don't know which people are the culprits and which are there on vacation, but they have a polygraph with 90% accuracy. How many casino patrons will be falsely accused of the theft? So there might be a few things to pick out. We want to know how many total people are here. And this is a horrible, what is this, Ocean's 11, Ocean's 12? But he's not Mr. Ocean, he's Mr. Seabody. So the total number of people that are here are 988 plus the 12 capers that are going on over here. So 988 plus 12, like I said, there's 1,000 total people here. And so this might be one of those questions that only kind of exist in a math class. It's got nice even numbers. And I'm doing that to kind of drive home a sort of point. So there are 1,000 people. We know out of the 1,000 people, 12 are lying when they get interrogated, and 988 telling the truth. They have a polygraph with a 90% accuracy. Look at there. Okay, and so they have a 90% accuracy. The 90% of the 12 that lie will get detected and caught when they lie, is what this is saying. So 10.7 is what this is giving me. So since we don't want to quarter someone, we'll probably just round it up to about, there'll be about 11 people. So about 11 of them will get caught when, like, what, one of them, maybe 2 of them will get away if they get lucky and round off this 0.7, right? But probably 1 person caught, and then 1 will get away. You could also do 10% would be the other half of the 90. 10% of 12 would give you 1. Okay. So now we're thinking about the people telling the truth. Well, 90% of those people telling the truth will be set free. They will be told, hey, you're being truthful. So that gives me around 898 truthful. And these people are going to be let go. So you can do 10% of 988, or you can do 988 minus 899. But either way, you should get that 99 people are being falsely accused. So congratulations, you've just convicted 99 people falsely to convict 11 people that were actually guilty. So this does not seem probably like the best way to go about interrogating people. Probably also a word of advice, like polygraph tests are not administered, admissible in like in most courts. I think every court, pretty much, any reputable court for sure is not going to like accept a polygraph. They are like severely flawed, and a lot of it's just interrogation tactics that they pretend like there's a sort of science behind it, and it's not really as much as science is what they want to say sometimes. And there are ways to cheat polygraph test as well. So we have one more sort of example on testing, and then we have one more sort of example on political math. And so we're looking here. We have another test. Suppose a high school wants to implement a drug test for its student athletes. The drug test is advertised as being 96% accurate. If we assume that 5% of athletes actually use drugs, then how many athletes that test positive for drugs are falsely accused? And so you might notice there's some information that they're giving you here that like you probably wouldn't know, right? We know 5% of the athletes actually use drugs. Like, where are they getting this from, right? So there are certain things, there's certain assumptions and certain figures that they figure out. There are ways to estimate this and get very close estimates to these numbers. But with that said, they're going to have to give you quite a lot about like reality and stuff of that nature around you. The drug test is advertised as 96% accurate. So where are they getting this 96% from? I believe it's the 48 out of the 50 is where they're doing it. Given that they use drugs, what are the odds that it will pick it up? So 48 out of 50 will give you the 96%. We assume that 5%, where we get this number, 50 out of 1,000 will give us the 5%. 48 out of 50 is what's giving us the 96%. And 50 out of 1,000 is it's giving the 5%. So just a quick sort of review on where that thing is coming from. How many athletes test positive for drugs were falsely accused? So now we're narrowing this thing down. We only want to look at one row, one column. How are they saying it? They tested positive. They're giving us that they tested positive. So they're giving us that they tested positive. We should be only looking here. Given that they test positive is what they're saying. What are the odds that they didn't do anything? Okay. So this is 38 out of 86, right? And we look at 38 out of 86, 44% of the positive results are false. And so this goes back to saying we have 1,000 students. You found and you convicted a total of 48 students, and you correctly like convicted them of using drugs when they were, but you also incorrectly accused 38 students. So this is a pretty large number. 44% of the people that you actually accused were innocent, right? And so there's a large proportion of innocent people there that you're kind of crucifying in order to get this drug test passed. So another sort of thing with our judicial system, right? I can't remember. There's this sort of test, and then there's the reality. It's how these sorts of things, these tables are kind of based. So the test either says you're positive or negative, and in reality, you either did it or didn't, right? And so in our court system, this is like your court. Court says you're guilty, you're deemed guilty, you're innocent. And then in reality, you either did the crime or didn't crime. Real proper English there. But you didn't commit any crime. Okay, so this is sort of the way that you can also think about things. So this one, if you did the crime and you were found guilty, good, our court system worked. And if you were innocent and or didn't commit the crime and found innocent, good, our court system worked. And let me look. Okay, and then this one is called they call this a type 1 error, a false positive. Sometimes in the statistics you'll see type 1 error. I think they represent it with alpha, and I think this one's represented with beta sometimes. But this is type 1 error, this is type 2 error. So this would be a false positive or false negative. Is that what that is? I believe. Yeah, false negative when the test says you didn't commit the crime, but you really did, right? And so if we're looking at this, this is the sort of thing, and this is probably pretty similar to the drug test. They did drugs or didn't do drugs. The test came up positive or negative, right? We have the same sort of error happening here. So if you think about how our court system works, it is that sort of you're innocent until proven guilty. So if we think about these two types of errors, there is a sort of trade-off. The more of this one we have, the less of this one we have. And the less of this one we have, typically the more of this one we have. Because this is the reality of the situation, but this is our decision. So as a judge, if you're thinking about a judge sitting up on his bench, if he's just going out and he's just saying guilty, 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 guilty all the time, he's going to have a lot of type 1 error, but his type 2 error will be like really small, right? It will be reduced. The other way around, if a judge is just letting people off, he's just like, yeah, you can go, you can go, you can go. Our type 2 error will be really large, but our type 1 error will be small. So sometimes there's a sort of trade-off that you get between these two errors, and which one you want to sort of want to be larger. And so in our system, we tend to prefer type 2 error. We would rather have a system that fails to convict someone than a system that convicts someone unjustly, right? Is what we're supposed to like rely on. Maybe everyone doesn't get that sort of treatment, and that's a separate conversation. But the way it's written and the way that they claim to be, you are supposed to be innocent until proven guilty, right? And so we really try to make this one larger and not convict people innocently. There tends to be what we would consider probably more injustice in convicting someone innocently than allowing someone to get by with a crime, right? Usually they commit one crime, they'll commit another, they'll eventually get caught anyway. What goes around usually comes around, even if it takes some time, right? Okay. Suppose federal government spending for a popular education program was $100 million this year, sorry, and that Congress proposed an increase to $102 million for next year. Explain how this can cause lobbyists who oppose the program to complain about the size of the increase. Assume the CPI is expected to rise by 3% over the next year. So this is getting into you can phrase things and you can kind of pick your numbers sometimes to represent certain things. There are certain biases that exist within systems, right? And certain biases that exist within us as individuals. But we want to think about if you're a politician trying to spin this stuff, if you don't want to spend money, what might you say about this? So suppose you're going from 100 million to 102 million. You're going to say, oh, holy cow, we went up 2 million increase. That's a $2 million increase. And that would be a true statement, right? And there might be like some valid reason. That's a lot of money to spend. That's a good large amount of increase. But then if we think about the relative change, right? If we think about we're going from 102 or from 100 to 102, if we think about that relatively to our entire budget, this is only going to be a 2% increase. And if we know anything, if we learned anything about that previous chapter from CPI, our CPI is 3%. And we can make an argument on why that is problematic. This increase is not even enough to account for inflation. So we're not even this isn't actually more money if we actually count for inflation. It's actually less money than we spent previously. So this is another one of those things. Do you want to not spend money, or do you want to spend money? And how do you want to look at this, and how do you want to analyze this? Because this is a true statement technically, right? But this is also a true statement. And if I were being honest, I feel like they put these both these interpretations up on a same pedestal. To me, this is a better interpretation. If you really want to talk about how much you're spending, you have to know how much you're spending relative to the total amount. This is only 2% increase, and the CPI is going to increase 3%. You're not going to be able to keep the same budgeting and the same standards that you did if you're not keeping up with inflation. Like this is kind of the bottom line, right? So I would typically think this is a better analysis, even though the book tries to say they're both kind of on the same page. I don't think so. I think this is definitely a better numerical analysis and a better argument to be had here. But that might also be my own personal bias. So who knows? I don't think looking at just the raw amount, the absolute difference is really representative of what is happening. But it's a true statement. And if I wanted to complain about $2 million increase, $2 million is a lot of money, and I could really complain about that. It's not a false statement, right? But there is a certain bias that can exist in how you look at things. And with that said, not all biases are created equal either, right? Like I said, I do believe this is a little bit better of an interpretation. So, but that's why you're here to learn about how to analyze reality and try to be just as confused about it as I am. So let's go about it, and I will see you next time in class. Have fun, study hard, and see you.